Okay, so I think we
understand what we have.
okay. Let's go again about this problem. Okay, so in general, I gave you this problem. I said, okay, we have some bubble, and bubble, you know, have water on the outer shell, water with soap, and all the charge is over here in the outer shell. Okay, and this is a symmetry problem. Okay, I know that the location here, let's do it in a different color, the location here must have the same property of the location here, and the location here, and the location here, and the location here, and I gave you the hint that if you saw spherical, cylinder, infinite plane, probably Gauss's law gonna work. This is one of the cases. Symmetry, nice, like it, and you would like to choose and solve this with Gauss's law. But then I came and said, I'm gonna fuck you up. I'm gonna put here a small charge, and this charge gonna produce electric field which is in all direction, also in these directions. So right now the symmetry is lost, because this was dA and the electric field is, I don't know, something like this, right? And dA here is this, but the electric field is something like this. So if you try to solve Gauss's law, for example, choosing a sphere, you had E only in one location if you choose this sphere, which is R in the middle, dA, but right now you have so many angles that you're gonna be confused. You cannot solve it. And then I told you something. Let's use the spatial sauce inside the box. That was the superposition principle. The superposition principle tells you this. You don't need to solve this crazy problem. You can divide it and say, okay, the electric field, the real one we have in the world, according to the superposition, equal to all its contribution. Electric field of the bubble plus electric field of the charge. You can calculate them separately and then sum them up. If there was only bubble in the world, I know that this equal to Q in A divided by epsilon 0. This is equal to 0. This is true with the charge, without the charge. But right now, I know that these lines are not exist because it's a superposition. All the electric field is gonna be due to the surface of the bubble, and they all gonna make electric field that go inside according to symmetry, right? Inside, inside, inside. They're gonna repel. Repel, this is a plus, right? So the angle for all the dAs, where the dA is pointing? Outside, right? So dA is pointing in that direction. The angle between them is minus 180, it's 180, right? Cosine of 180 is minus 1. So this is a constant. It's hold for all the dAs, okay? In all the dAs, it's ER, okay? ER can go outside, right? With this minus from here, and the integral of the dA is actually the area of the sphere, which is 4 pi r squared, which you should remember by heart. I know that the flux is equal to 0. I don't know if the electric field is equal to 0. Okay? I need to save it. I need to take it out. Take it out, equal to 0. Oh, this is constant. I can divide. Yes. ER is equal to 0. But this was a superposition problem. It was true only if the bubble is in the world alone. Okay? We solved this. This is 0. Right? What we left with, if you understand what is the electric field of a point charge, which we know thanks to Coulomb's law, right? K Q divided by R squared. So this is the answer, okay? So many of the times you're gonna have problems. For example, infinite plane. Yes, infinite plane is Gauss's law. But then they're gonna say with the holes in here, and in here. What you gonna do? You're gonna do superposition, make it a normal infinite, make this as a cylinders, infinite cylinders, and then you're gonna sum all the results out, okay? That's a concept.
Great.
Not symmetry, use superposition, have a symmetry, bring it back together. Concept I understood?
I don't understand why the electric field of the bubble is 0. I can understand inside, but what about outside? We're talking about what Q feels.
But they ask you what is the electric field inside the bubble. It's a valid question. What is the electric field outside of the bubble? Truly hot.
What Q feels.
No. The question was what is the electric field inside the bubble? And again, if it was outside of the bubble, same concept. You're going to say, perfect, Gauss's law, I have a symmetry, let's do it. And then you're going to say, oh, fuck, a point charge. What are you going to do about a point charge? Then you're going to say, aha, I'm going to use superposition, have two easy separate problems. Solve each one, sum up the results. So you would do a Gauss's law outside of the shell. The electric field would not be a 0. It actually would be the electric field like this was a point charge. We did it in the previous introduction. And you're going to sum this one with this one. Okay? Also look like a hard question, but superposition, kill it.
All right.
Clear?
Thank you.
Good.
I have another question about DA, but I don't know if you know.
Go ahead. Another question about DA.
Just like when do we use if it's a DA double integral, and when can we use just like the known equation? Like if it's a plate.
Yes.
When can we use pi r squared as our A? And when do we use dA is equal to, what is it, RD theta? dA is always equal to two variables. It could be dx, dy, dz, dx, dr, rd theta, dr, dz. It could be many things, right? But what you need to remember is, do I need to actually solve the integral? Like doing that, something is here, then put the two integral variables of dA's, or maybe here there's something that I can pull out, and then just calculate the whole area. Because if you can get to this term, and here, so it's just A. So this is the concept. It's depend on how much the problem is complicated. This is a more complicated scenario. When the charge density depends on theta, you have to have a theta in your dA.
It's not only in a charge. It also could be on electric field. We saw it.
Yeah.
Now you have 2D integral on area integral on the electric field. We have it here. Yeah. Okay, but from the first tutorial, yes, we also can do it on charge.
And one last dumb question: when the Q equals charge density times area, you take the derivative of both sides.
Again, don't for the camera.
When Q is equal, Q is equal to charge density times area, right?
Q equal. So when Q equal to charge density.
So rho whatever times area, right?
Okay, sigma. Yeah, times area. What about it?
Take you derivate both sides, take the derivative of both sides. You get dq equals...
you mean you want to see small chunk. What effect of the small chunk?
Exactly.
Yeah.
Yeah, my question is, why is the derivative only on area and not on the sigma?
Okay, so this step was not a derivative. It's important to understand. It was not a derivative.
Small chunks.
A small chunk. If you look at the big thing, okay, so you see that I put here not, which means it's a constant. So this is all when things are constant, okay? Otherwise, you can only do that. This is the step. It's not integral on dq, okay? This step is not a derivative. Derivative, it's when you see the differences between two and compare it to time. This is not derivative, this step. This is a specific example of a situation. This is a general idea. This is always hold, okay? This is specific case.
Even when sigma is not constant.
This is hold when sigma is not constant, exactly. This is the general case. This hold only if sigma is constant, okay?
Yeah.
Good.